All right, the next part of this is differentiating a composite function. So we've obviously already looked at composite functions. What we talk about, what we're basically doing with a composite function, it's a function of a function. So it's something that's applied to an x basically before some other thing is applied to that x. So to differentiate a function such as y equals 2x minus 1 all squared, the best way to do this one, this is a composite function, but the best way to do it is something if it's just squared, you can just multiply it out, okay? However, what we're looking at going forward is something like 2x minus 1 to the power of 7. So basically something with a bigger power. This is a bit more difficult to do. We don't want to have to do 2x minus 1 times by 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 2x minus 1. We can do that. It's a bit more difficult than we'd particularly want to do. So there's a shortcut, obviously, involving not actually multiplying it 7 times, okay? This is what we call the chain rule. So this is a big part of advanced higher. We're just going to touch on it when we get to higher, okay? So there's several different methods that people use. There's certain shortcuts that you can use, but basically what you're doing, this won't make any sense to you, okay? But if you've got f of g of x, then the derivative will be f dash g of x times by g dash x. In other words, what we're doing is we differentiate what's outside the brackets, okay? So if we're looking at this one up here, we'd basically do as we differentiated before, we'd multiply by 7 and then drop that power by 1. And then what we have to do is multiply by the derivative of what's in the brackets, okay? So in this case, we'd have to multiply by 2 as well. It's a very easy thing to forget, and a lot of people do when you get a situation like this, okay? So basically, to stop us forgetting doing this, I'm going to give you a formula so that it becomes more inherent to you, I guess, that you have to do this with this kind of situation, okay? So by the laws of fractions, so up until this point, you've kind of thought of probably dy by dx as just, I am differentiating now, okay? But what it means is it's the change in rate of y with respect to the change in rate of x, okay? So dy is actually a thing. So the change of y divided by the change in x, okay? So if we look in terms of fractions, we can say that's the same as dy by du times by du by dx, okay? So two different derivatives multiplied together. And the reason it works is obviously these du's would multiply out, okay? Or sorry, simplify, okay? So they cancel each other out, in which case we'd just be left with dy by dx. But obviously we've just kind of brought this du in from nowhere. But what that is a function in terms of u, which is basically going to be the function that we have inside our bracket. So most of these situations where we use a chain rule, in higher at least, you're going to have something in the brackets and then a power outside the brackets. So what we're basically going to do is the function that's inside the brackets we're going to call u, okay? And what we're going to do is we're going to differentiate outside the brackets and differentiate inside the brackets, okay? So in this case, using this kind of general form here, you've got two functions. You've got ax plus b, or as the first part of the function. So we're going to call that u. U equals ax plus b. In which case, the original function becomes y equals u to the power of n. Okay, that's all I've done there. So these are our two functions, and because of these two functions, we can now find du by dx. So we can differentiate u with respect to x. That's this bit here, and then we can find dy by du. We can differentiate y with respect to u. We can find this bit here. And then at the end of it all, if we times them together, what we'll have is what we wanted in the first place. We'll have dy by dx, okay? So you don't have to write it like this every single time. You basically got to know what you're doing. Okay? Yeah, so if you actually differentiate these things, you get that. Yeah, that's just a bunch of stuff. Yeah, ignore that one. Right, differentiate 4x minus 9 to the power of 6, okay? So going by the method I've just said, what I want you to do is let u equal 4x minus 9. We're letting it equal that because that's not the question, what the question asks us to do, but it's going to help our working. So we're going to take the bit in the brackets, the 4x minus 9, we're going to take it out, and we're going to make that equal to u. So u equals 4x minus 9. Therefore, if u equals 4x minus 9, the original function y equals, it should probably be a y equals here, would equal u to the power of 6. So y equals u to the power of 6. So now we've split this kind of composite function, which is by definition two functions combined together. We split it into those two functions. So the 4x minus 9 and basically the power of 6. Okay, what we're going to do is we're going to apply the chain rule. This is the chain rule, okay, and we're going to basically differentiate each one individually. So 6y dy by du, sorry, so this one differentiated with respect to u would be 6u to the power of 5. The first one, du by dx, would just equal 4. So this one differentiated with respect to x would equal 4. The point being, if we're going to find dy by dx, it's those two multiplied together. So 6u to the power of 5 times by 4, which is 24u to the power of 5. Right. Easy enough. But the thing with this is we let u equal 4x minus 9, and u is in our answer. Okay, if a mark is marking this, they're thinking, well, what the hell's u? Okay, even though we've made that clear, we still have to kind of actually finalize our answer. The answer that we're looking for is in terms of x. What we've got here is not in terms of x. So all we actually need to do now is basically put our u function back in. Okay, so we're going to take the u out and put 4x minus 9 in instead. In which case it becomes 24 times by u, which is 4x minus 9 to the power of 5. Okay, right, there are shortcuts to that, okay, but you just have to remember to use those shortcuts. Okay, and what most people will do in a situation like this is they'll just say it's 6 times by 4x minus 9 to the power of 5. Right, it's not as simple as that. You have to differentiate what's in the brackets as well and times by that. If you can remember that, then fine, you don't have to go through all of this, but I suggest until such a point as you get used to that, you go through these stages. Okay. Right, so a slightly different example for you now. Y equals the fourth root of 5 minus x to the power of 3. Right, the point in this one is it's not in differentiable form. So we change it into differentiable form first. So that's 5 minus ax to the power of 3 over 4. Okay, right. Let u equal 5 minus ax. Okay, so take the bit in the brackets out. Let u equal that and differentiate. Or no, so before we do that, we'll say that y equals u to the power of 3 over 4. Okay, we're going to differentiate each one individually. So du by dx is minus 8. So 5 just disappears, it becomes 0 minus 8, or just minus 8. This one would be 3/4 u to the minus 1/4. Okay, so then obviously our overall derivative is these two multiplied together, which however way you choose to do it, you might want to simplify this first, but it's 3/4 of u to the power of minus 1/4 times by minus 8. Which is minus 24. So the minus 8 is times by the 3. So that gives us minus 24 over 4. And the u to the minus 1/4 becomes 1 over u to the power of 1/4, which simplifies. Minus 24 over 4 is just 6. So it's minus 6 times by this. U to the power of 1/4 is the fourth root of u. Seems confusing. If you having this as a video, as a PowerPoint, is that you can go through it in your own pace. Okay, but the problem with this at this stage is that we've still got our u. We want to take our u out, replace it with 5 minus 8x to get our final answer. Okay. Right. We also have chain rule in terms of our trigonometric functions. Okay, so when we've got k sine x and k cos x, we can use the chain rule. In other words, when we have a 2 or 3 or whatever it is, a number in front of our x. So again, you've got to be very, very aware of this. It's not going to say in the question, you need to use the chain rule here. You have to spot where you use the chain rule. So what we're doing with our x is we're timesing it by 2, and then we're finding the cos of that, or 5 times the cos of that. So there's a function of a function here. Therefore, we use the chain rule. Okay, and this works in the same way that I've just shown. And this is why it helps to use the whole dy by dx equals dy by du times by du by dx method, because this is not a case of doing outside the brackets and inside the brackets. This one we actually have to think about. Okay, so we're going to let u equal our initial function, so the 2x, in which case y would equal 5 cos u. Okay, we're going to differentiate each one. So 2x differentiated is just 2. 5 cos u differentiated is minus 5 sine u. Okay, remember you got your formula sheet for that. In which case dy by dx is those two times together, which is just minus 10 sine u. And all we need to remember at the end is to replace our u with 2x. So you can see a formula there. You can see a kind of a cheat there, a shortcut. We're basically just multiplying by this number here, because the derivative of 2x or 3x or 4x, whatever it is, will always just be that coefficient. Okay, so as long as you multiply by that, and then just make sure you actually differentiate the cos appropriately, cos differentiates to minus sine, then you can get that right. But there's a lot of mistakes that can be made. Trust me, you know how long I've been teaching in all my 45 years of life. There's lots of mistakes that can be made, so I suggest you go through with the steps that I've shown you here. Okay. Yeah. Oh yeah, your formula sheet actually looks like that. So it does actually tell you this. So you don't even need to really worry about this at all, because your formula sheet does tell you this. So the previous one that I showed you in terms of sine and cos, is not what's actually in your formula sheet. It's more this version, which does actually lend itself nicely to your chain rule. Okay, but again, you've just got to remember this there and remember to use it properly. But if we have something like this, it's a little bit more difficult. Okay, so this is not in your formula sheet in any way, shape, or form. This is a sine to the power of 4x. Right, the first thing we've got to remember is what this actually means. Okay, if we have sine to the power of 4x, it means sine x to the power of 4. Remember, we just don't want to write sine x to the power of 4 without brackets because that's implying that the x is to the power of 4. So the whole thing, sine x, is to the power of 4 here. Okay, so this one we can go back to that original kind of shortcut. We can multiply, we can differentiate outside the brackets and then differentiate inside the brackets. But nonetheless, I'd still recommend using this method. So let u equal sine x, in which case y equals u to the power of 4, differentiate, differentiate. Sine x differentiate is cos x, u to the power of 4 differentiate is 4u cubed, and then we multiply these two things together and we get 4u cubed times by cos x. Okay. Then we take out the u, replace it with our sine x, in which case it becomes 4 sine cubed x times by cos x. Okay, and obviously there's a couple of ways of writing that. You could have put the cos x in between, but 4 sine cubed x cos x is what you're looking for the derivative of sine to the 4x. Okay, so I'd recommend using the chain rule as I've done it here, but if you want, you can find a shortcut. But I think for this one, a lot of people would forget to multiply by the cos x.